Oh, yeah, what's up? Oh, question over something?
Yeah, I just don't remember where we got this from. I was looking at it and I don't remember where we got this from after we did this.
I don't even know what this is.
X was a constant in the problem. Oh, that's n. That's supposed to be n going to infinity, not x. So x is treated like a constant.
Storage starts.
There was an employee that yelled at me the other day at McDonald's.
So when you're taking derivative of this, that's x times n to the negative 1. Negative 1 comes out,
Literally walked in.
then you have n to the negative 2, right?
This is like completely real.
You sure?
This is a McDonald's.
This right here?
Yeah.
Okay, but the x is a constant, so it just comes for the ride. So
Oh, okay.
that's why.
In the kitchen,
That makes sense?
I don't know what's going on.
Okay.
Just like I see arms like.
But it was so hilarious. It was so cool. Like to die. That was something.
Yeah, that one works out really well.
Yeah. Really. I literally walked. It's about like 30, 40 minutes. Just talking about those.
The kid did that one also for us, for my classmates. Yeah, it just shows the bad account.
Giving you a hard time already?
I forgot my battery for my laptop. So
You have to go through the computer.
I have to use the computer, yeah. Dang it.
If you have the charger, you can just plug it without the battery. If you have the charger,
I don't have the charger. That's what I forgot.
both.
Yeah. I have the laptop. I just don't. No. We'll use that.
No, she's asking about something. But actually, it might actually be good for her. No, that's the.
That's what we discussed.
It's a page.
Okay, let's get started. I forgot my charger for my laptop and it's almost dead, so I'm having to use the PC here. And fortunately, it already has the program so we can view my lecture notes. Hopefully we won't have any issues. I have your quizzes from last time. I'll give those back in a little bit. Let's go ahead and get started though. How'd that L'Hopital's rule homework go? It's a lot. There's some pretty messy problems in there, right?
Yeah, like towards the middle.
Yeah. I was thinking about it on my way here. I was like, man, I really hope they're all doing their homework.
It was that one where you had to like continue, or you continue to expand it out.
Yeah.
It got like really big. Yeah, that one.
They can get really bad. Okay. Yeah, I was thinking, I hope that my students are doing their homework and not procrastinating and all that. And then I was thinking, well, it's college. They should know this by now.
You know me.
But, okay. So we are going to move on, but I wanted to just kind of do a quick little recap of what we've done. Not the whole thing, but specifically 3 different things that we've done where some students seem to get confused. So let me break up the board into 3 sections here. These are 3 completely different ideas that we've talked about since the last test. If we have something like xy squared equals cosine of x plus y plus 1, we can try and find y prime. That's one type of problem that we could see. Another one is something like y equals sine of natural log of x squared plus 1. That's a different type of problem. And in this, let me add one other type of thing. Y equals x plus 1 to the 4th times x minus 1 to the 5th over x plus 3 to the 3rd times x plus 9 to the 7th. And then last thing is something like limit x goes to infinity of x sine of 1 over x. Okay, so the reason I wanted to put this up here just to make sure we all can like recognize what we're supposed to do when we see something. So what are we supposed to do if we're trying to find the derivative of y here with respect to x if we have something like this? Implicit differentiation. All right, so this is an implicit differentiation, which means you take the derivative of both sides of the equation with respect to x. All right, how about this one right here? You just differentiate it, right? The only thing here is that you need to know what the derivative of a log is, right? So we did an entire section on derivatives of logs and exponential functions. So this is just straight up derivative, just you need to know the formulas for derivatives of exponentials and logs. This one was different though. This was logarithmic differentiation, and that's where you take the log on both sides of the equation, right? Okay. So all of these are just finding derivatives, right? Then we got to something like this. This is not a derivative, right? This is a limit. But to take this limit, we're actually going to need to use L'Hopital's rule. L'Hopital's rule requires that we take derivatives. So you just want to kind of keep a broad kind of perspective on what's happening here. This is a limit problem that requires differentiation to do it. These are differentiation problems. This one requires implicit. This is just straight up derivative. This one, logarithmic differentiation. Okay? All right, so we're going to proceed now into chapter 4. Is everybody tired? Yeah, that storm kept me up last night. All right, so I have to use the computer here, so I don't have my mouse, a wireless mouse. Is this it? Okay, so we are starting chapter 4, applications of differentiation. So finally we get to do some things with this derivative. We are going to talk about finding the maximum and minimum values. This is a very important topic. The mean value theorem is very important, but it doesn't come up much. I mean, it's important if you're like a math major. The mean value theorem is an important thing. But in terms of here, we just want to introduce the idea and then move on, all right? And then what we do is we talk about how the derivative helps us determine what the graph of a function looks like, the shape of a graph. Somehow the derivative helps us actually determine what the graph of a function looks like. Then we're going to actually use that information to sketch some functions, but we're going to sketch some functions that are rather complicated functions. I mean, in your history of sketching functions in your mathematical life so far, you've sketched lines, you've sketched parabolas, you've sketched polynomial functions, you've sketched rational functions, exponential functions, and logarithmic functions. Those are the seven groups of functions, although you can put lines and polynomials. Sorry, lines, quadratics, and polynomials are all the same. They're all polynomials. So really you've done polynomials, rational functions, exponential, logarithmic functions. That's what you have some background in terms of sketching functions. We are going to open that up to functions that fall into none of those categories, that are maybe like some weird combination of a polynomial along with a trig function. Oh, I forgot the trig functions. Yeah, sorry, trig functions. So, so we're going to tackle some pretty interesting looking functions. And then we will finish the chapter off with optimization. And optimization problems are word problems. So do you remember the related rate problems? You know, the sphere is growing at a certain rate. Okay, those are word problems. They were somewhat of an issue. I still need to send you home with some problems. These are, again, going to cause issues because they're word problems, and I think just naturally most people have trouble with those. But this is probably one of the most useful types of problems that we see in this class. How do we optimize something? So we'll get to that, all right? But we start off today with maximum and minimum values. So I'm going to follow my lecture notes so long as this works. Okay. So we're going to start with the definition of what's called the absolute maximum and absolute minimum values of a function. So if we're given a curve f defined on some domain D and some number c in the domain, right? So we've got some function, we have some domain. So let's say you can plug in anything between, let's say, here and here, okay? So you got some curve in here. Then there's some number c inside here, c. Okay, so you got your domain and then some number inside of it. This says that f of c, that means the function's value at that c, is called the absolute maximum value of the function f on that domain D if f of c is greater than or equal to f of x for all x in D. What? Okay, this just means that is there a point in here, is there one, where when you plug that point into the function, it is the highest point on the graph. It is bigger than or equal to, right? The f of c is a y coordinate, isn't it? So this means that it's the highest, the biggest y coordinate out of all of the different y coordinates that can be found within that domain. If that's the case, then f of c is called the absolute maximum value. Now I'm going to show you the pictures with this, but these are the definitions. On the other hand, we call f of c an absolute minimum if it is the smallest value. It is smaller than all other y values of that function within that little domain. In either case, f of c, in either one of these cases, is called the global maximum or minimum, or sometimes the extreme values of the function. So these are different words you'll hear me saying. Absolute maximum, minimum, extreme values, global maximum, minimum, they all kind of mean the same thing. The only one that's a little weird is extreme value. If I say extreme value of a function, it could be the maximum or minimum. It's not saying which one, right? So it's more general, I guess. Okay. Now, we have a different definition of what's called a local maximum or minimum. Okay, so we just looked at extreme values. We looked at global maximum, global minimum. Now we talk about local maximum, local minimum. So again, you have some curve f defined on some domain D, and then you have some number c inside of that domain. F of c is called the local maximum value of f on D if f of c is bigger than or equal to f of x for all x, and here's the big word, near c. All right, in the last definition, this said for all x in D. That means this was the biggest, highest y coordinate for the entire picture, the entire graph on that domain. Local maximum, you just have to be the highest near C. And that's weird because in math, I think we've already talked about near is a very subjective word, right? I think I talked about, are we near SeaWorld right now? You know, are we near our sun, right? It's all relative. So this is a weird word, but I think once we see a picture of this, you'll get the idea. Local minimum is the opposite. It's the smallest y coordinate near some value c. So let's take a look at some visualizations of this. You know what? Can I reevaluate this? Okay, there we go. So there is a function, right? And it looks like it's defined, that looks like this is 5, this is 10, I know that's hard to see. Looks like it stops at 9 here. And over here, this looks like -7. So it looks like the domain here are all the values of x between -7 and 9. Do you agree? All right, so let's see. Do we have an absolute maximum? Does there appear to be a point that is higher than all other points on the graph? It looks like somewhere around in here, right? That looks higher than this point, doesn't it? So I would say that this right here would be a, let's say G for global max. Is that okay? Global maximum. Does it have a global or absolute minimum? Looks like out here, looks like at about -5, we would have a global minimum. Understand? The highest point on the curve, the lowest point on the curve within that domain. Yes? Okay, now, if there is a global max, you should only have one, right? I mean, like, there's only one highest value. And same thing with global min, there should only be one, at least in terms of curves that we normally deal with. Let's talk about local. So do you see a local maximum? So local max, the difference is that you have to be the highest point just near that.
The points is -7 and the points 9.
These two right here? So this point right here would be the highest point if you're just looking near this point. Now we can't look to the left. And the reason we can't look to the left is because our domain is restricted, right? So do you agree that that would be the highest point near here? Yes? So let's call that L max. That's a local max. Any other local maximums? The global maximum is actually a local maximum also. And then over here we have a local maximum over there on the end. Make sense? And then what about local minimums? Local minimum, right here, this one, right? This is a local minimum. It is the lowest point near that point. And then how about here? Local minimum. Does this concept make sense? Okay, so the way I think about it is like, if you have a graph that looks like this, okay, all of these points are local maximums, right? So it's kind of like, this guy's the king of the hill, right? Of this hill. This guy's the king of this hill, this guy's the king of this hill. But this guy is the king of all the hills, right? So this is the global maximum. These are all local maximums. Make sense? Okay. Now, the reason why we have to be able to distinguish between global and local is because some functions we're going to deal with will not have domain restrictions. And if you don't have domain restrictions, so look back at this graph. I'm probably going to show you another one of these in a second. But if I put arrows on the end of that, then there's no domain restriction. That means this graph goes like this forever and this forever, right? If these two sides went down forever, would I have a global minimum? I would not, because there would be no lowest point, because this keeps going lower and lower and lower, right? So I wouldn't have a global minimum, but would I have local minimums? Yes, I would have local minimums. So we need a way to distinguish between what might be happening locally as opposed to globally. All right, let's keep going. And kind of giving it away here already. Okay, global maximum, yes? Global maximum? Global minimum. What's this? local max, local min, local max, local min, local max and global max, right? Okay, so I don't think y'all seem to get this. All right, good. Okay, so for this one, assuming that these arrows go up forever, so no more domain restriction here. We have no global maximum, okay? So no global max. You cannot say that you have a highest point on this curve because it goes up on both sides forever. You do have a global minimum. And this is also a local minimum. This point right here is a local maximum. And then you have another local minimum. And is that it? I got everything covered there? Yeah? Okay. So it is possible to not have a global something happening. Okay. I think you get the idea here. All right, so now let's get on to a theorem, the extreme value theorem. If f is continuous, continuous means we can draw it without picking up a pencil, on a closed interval. So let me go ahead and draw this situation. I have a function that is on a closed interval a, b. So I'm only going to draw between a and b, and it's continuous. So wherever I start at a, I'm going to end somewhere. It doesn't matter. I'm going to end at b, and I have to connect these together with a curve without picking up my pencil. This theorem says that f attains or achieves both an absolute maximum and minimum value in the interval ab. So if I have a continuous function on a closed interval, it must have an absolute max and an absolute min. There's no way around it. And that's just because there's no way you can draw it without that happening. All right? So if I go up and then back down to this, something like that, well, yeah, that's an absolute max, that's an absolute min, right? There's no way to do it without guaranteeing at least one of those or both of those happening. Okay, what about straight line?
Yeah.
Local minimum, local max, right? Okay, so how about this? How about straight across? Your global maximum and global minimum are the same. Okay? Your highest point is also your lowest point, right? And your lowest point's your highest point, and it actually happens everywhere.
Oh my.
Right? So you have, now look, something to point out here. Your global maximum is the y value. Let's say that y value was, let's say, 5, okay? Then the global maximum of this function is 5. The global minimum of this function is 5, all right? Where does it happen? At what x value in here do I get the 5? Everywhere, right? So there are an infinite number of places where I get the global maximum and the global minimum, right? But there's only, there is a global max, there is a global min, they are the same. See, and it all goes back to that definition that in order to be a global max, what we needed was that f of c was greater than or equal to f of x for all x in the domain. The equality here is what allows this thing to work. Is 5 bigger than or equal to every other y value here? Yes. Is 5 less than or equal to every other y value here? Yes. So it satisfies both being a global max and a global min simultaneously. This is a weird example, but it just shows you it's still, everything holds, right? We don't have any problems with our definitions. All right, so this theorem says we are guaranteed the existence of both of those as long as we have a continuous function on a closed interval. Can somebody think of why we have to have continuity here?
That makes it a function.
No, functions don't have to be continuous. You can have breaks and gaps in them. Can you think of a function that would not be continuous and that would mess this thing up, so we don't have, we have to be defined on this closed interval, so you have to be defined everywhere. Tangent is not defined at the ends, like at the pi over 2, negative pi over 2, right? So you have an asymptote there, so it would not be defined on a closed interval. What I'm trying to say is, can you come up with a function that's defined on a closed interval but is not continuous and would violate this?
One that has a vertical asymptote, and so the ends go to infinity, negative infinity.
I think that's what you're getting at also. Okay, so let me address that. Let's say we have a function that goes like this. I'll go with the tangent. There's tangent function. Is this a continuous function? Can I draw without picking up my pencil? Okay, this is pi over 2, this is negative pi over 2. Is this a closed interval? Is it defined? Is it a continuous function on a closed interval? It's not a closed interval. This is only defined on the interval negative pi over 2 to pi over 2, with parentheses, not brackets. So, and this does not have a global maximum, but what I'm asking you is, can you think of a function that's defined on a closed interval that is not continuous, and therefore this theorem doesn't work? Square root? Okay, so let me erase this. Let's do, this is the square root function, right? This is like y equals root x. And I need to cut it off on a closed interval. So let me just say 4 here. Is that all right? That is a continuous function though, right? That is if we're only looking between 0 and 4. This is continuous, and it would have an absolute maximum and an absolute minimum. I'm not sure if I'm doing what you want me to do here.
What if it's like x equals 16, so it's not defined as 4? You know what I mean?
If x is 16 and then you get 4, what? I'm not with you. I'm not sure I'm stating what I want you to try. I'm trying to get you to think of why this theorem requires the function to be continuous. Why is that requirement in the theorem? Did you have?
I was going to say, because what if it was something that was isolated? We're just going up and down and down and down. Like you pinpoint something. I don't have an equation for it, but what I'm talking about?
Like if you just draw something without the equation,
Like whenever we're trying to find limits, it was isolating.
Oh, it was like.
Yeah.
Is it because asymptotes, some asymptotes create positive or negative?
Let me try and just start over. Let me start over. Let's say we have a function on a closed interval. That means it's defined at A, right? Because it says it's defined on a closed interval, and it's defined at B. I said that it must achieve an absolute maximum and an absolute minimum, right? Because I'm going to draw this without picking up my pencil. Yes? Is there a way you can come up with a function that is not continuous that you could draw that would not have an absolute maximum or an absolute minimum? Let me just put one up here. What if I draw this? Okay. Right? Now, does this have an absolute maximum?
No. Yes.
Okay. Is this defined on the entire interval? At every point, is there a y value? Yes? Okay. Does it have an absolute or global minimum? Let me move this point up a little bit. Does it have a global minimum? Appears it does, right here. This one right here. Global minimum? Yes? Does it have a global maximum? Is this the highest point on the graph? No, because these points are on the graph, right? Do you agree? And let's say, just for the sake of demonstration, let's say that's 5. Is the global max of this function 5? No. Because there's a hole here, right? So what is the limit as I am approaching that from the left? It's approaching 5, right? But does it get there? No. So you cannot say this has a global maximum. Let's say you say it's 5. The global maximum is 5. Let's say you say that. It never achieves 5. So you can't say that, right? So you say it's 4.9. Well, I can just move a little bit closer and I'll be higher than 4.9, won't I? So you say it's 4.99. And so I move a little bit closer and I get to 4.999. Yes? There is no number that you can say is the highest here. Does that make sense? So there is no global maximum here. The theorem requires the continuity. As long as you have the continuity, then you're guaranteed the absolute max and min. Diego, you said piecewise, but I was trying to answer a couple of other questions. I did hear you. All right. As long as we got a continuous function on a closed interval, we have absolute max and min. All right. I can skip that. All right, now let's move on to another theorem. This theorem is Fermat's Theorem. Have y'all heard of Fermat? Fermat has a famous theorem. It's called Fermat's last theorem. This is not it, okay? Fermat's last theorem was something that this guy Fermat scribbled in the corner on the edge of a book. And it was... He didn't put the proof for it. He just wrote down his conjecture and he said, oh yeah, I could prove this. But he never did, and we did not prove that until about, I don't know, about 5 years ago, I think.
No, it was like 1994.
Has it been that long?
Yeah.
Jeez, 10 years ago, sorry. It's been like 10, 15 years. That's how long, and this guy lived, I believe, like in the 1700s. So he scribbled this thing down, said, oh yeah, I could do this, but I don't really have the time to do it right now. And it took us forever to figure it out, but he was correct, actually. All right, so the same guy, but different theorem. It says if f has a local maximum or minimum at a point C, if it does, so if you have this curve and it has a local maximum or a local minimum at some point, and the derivative exists, then the derivative is 0. All right? This theorem is very important. It states that if our function has a local maximum minimum and derivative exists, then derivative must be equal to 0 there. This is saying, let's say I have a function. Let's say this right here, I tell you that that's a local maximum. That's all I'm going to tell you, is that it's a local maximum. And this is happening at some point C here. And the derivative exists. That's very important in the theorem. The derivative exists. Then the derivative must be 0. That means if I take the slope of my tangent line, the slope of my tangent line has to look like that. So you can imagine you have a local maximum like that, right? Yes? So I'm going to challenge you again. Why is this in here? The derivative must exist. So I'll state that a different way. Can you think of a function that has a local maximum at C where the derivative is not 0? So I'm telling you right here that this is a highest point on the curve locally, but the derivative at the top is not 0. Good. A point, a corner, or a cusp. What if I had, I'll do a cusp because I like cusps better than corners. What if I did that? Is that point a local maximum? Yes, it's a local maximum. Does the derivative exist there? No, it does not, because derivatives at corners don't exist. We talked about this before. So the theorem, we cannot draw the conclusion. The derivative will not be 0 here. So we have to have this condition. If we have a local maximum at some point C and the derivative exists, then the derivative must be 0. Okay, so I say that right here. It does not say that that if the derivative is 0 at a point, then we are sure to have a local maximum or minimum there. This is, I can't understate this, all right? This theorem does not say that if the derivative is 0, that we are at a local maximum or minimum. That is not what it says. So let's try and understand that a little bit. Can you think of a function where when you draw it, let's say at some point C, you have some point here, and the derivative is 0, but that is not a local maximum or minimum? What the shape of that graph could look like? X to the fourth power? X to the fourth should look almost like a parabola. Oops, like that. And so like here, that would be a local minimum.
Yeah, I know what I mean. Something like that. That would work, because this...
No.
No.
No. Anyone else? I think the marker was an indicator that. What do y'all think? We just talked about one. We just did one. We just had one up here a second ago. A cusp would. I'm saying the derivative is 0. Okay, I'm saying the derivative is 0, but draw me a function where the derivative is 0, but that's not a maximum. There you go. Something like a tangent function, or x cubed. See, look at the derivative. What is the derivative here? Is it positive or negative? Positive. And then you get to here, and what? The derivative, just at that instant at C, it's what? 0, and then it continues to be positive, right? So this is an example of a function where at C the derivative is 0, but you do not have a maximum or minimum there. So the theorem is saying that if you have a maximum or minimum and the derivative exists, then it must be 0. It is not saying if the derivative is 0, then you must have max min. Are we clear on that? Okay.
I forgot to read the local part. I thought it just meant...
You were thinking global?
Yeah.
Okay, so there it is right there. There's an example that doesn't work. There's that other example with the corner of the cusp. This is an example of that theorem where it does work. If at this point the derivative, if you have a local max and the derivative exists, then it must be 0. If you have a local min and the derivative exists, it must be 0. All right, so that seems like it may not help us, that theorem, but we are going to be able to use it. So critical numbers. This is another definition. Critical numbers. A critical number of a function, f, is a number c that is in the domain of the function such that one of these two things is true. Either the derivative is 0 there, or the derivative doesn't exist there. Anywhere that happens, that value c is called a critical number. Okay? They are critical because we need them in order to figure out where these local max and mins happen. They're going to be critical in our analysis. So what we get here is the final version of that theorem that says if f has a local maximum or minimum at the point c, then c is a critical number. C must be a critical number. All right, so here it is. End of the day, this is what it all comes down to. this right here. This is what it's all about today. This is what we're going. If I want you to take anything away from today, this is it right here. Okay? How to find the absolute maximum and minimum values of a function on a closed interval. All right. And I should have put here continuous. Yeah, it's right here. So, to find the absolute maximum and minimum values of a continuous function on a closed interval AB, to do that, here's what we're going to do. We're going to find the critical numbers of the function. What does that mean? We're going to take the derivative and we're going to figure out where the derivative is 0 and where the derivative doesn't exist. Then we're going to evaluate our function f at those critical numbers. We're also going to evaluate the function at the endpoints of the interval AB. We're going to compare the answers. The biggest value we get is our absolute max. The smallest we get is our absolute minimum. And that's the method. This is called the closed interval method. Right? We do this when we're trying to figure out the absolute maximum of a function on a closed interval. So let's do some examples. Okay, so I'm just going to make one up. Find absolute max and absolute. I'm using ABS for absolute instead of global. They're the same thing though, right? Find the absolute max and absolute minimum of the function f of x equals x cubed minus 5x squared plus 4x on the interval -1, 2. Now let's just take a step back to appreciate what we're about to do. I've given us a function, right? I've told you you're only allowed to plug in the numbers between -1 and 2. And I want you to tell me the biggest value that's going to come out of this function and the smallest value that's going to come out of this function. That seems like a rather difficult question to ask, right? In like college algebra, that would be kind of overwhelming, don't you think? Like, how do you figure out what the biggest and smallest values of this function are going to be? That's what we're about to do. So we need to start off by first determining, does this qualify for the closed interval method? Do we have a continuous function on a closed interval? Do we? This is a polynomial, right? Our polynomial is continuous. Yes, when we talked about continuity, there was a section where I said, you know, what functions are continuous? All polynomials are continuous everywhere. So this is a continuous function. We are on a closed interval, so everything's good to go. First step, we're going to find the critical numbers. In other words, we are going to find where the derivative is equal to 0 and where the derivative does not exist. DNE does not exist. All right, that's what I'm going to do first. Well, to do this, I need the derivative, don't I? So let's just take the derivative real quick. The derivative of this function is 3x squared minus 10x plus 4. So now what I'm going to do is I'm going to say, where is this thing 0 and where does it not exist? Let's start with the easier of those two questions. Does this derivative ever not exist? Is there any problems with this function? It's a quadratic, right? Quadratics are well-behaved functions. In fact, I can plug any number I want into this. The only problem we would ever have here is if perhaps we had division by 0, or we had like a root of a negative, like root of a number, and it could be negative. So polynomials, the derivatives are very clean, so there's no issue here, right? So I'm going to do that first. F prime does not exist. I'm going to exit out, and I'm going to say, because, you know, this is since f prime is a polynomial. Well-behaved function. Now the second part, which I saved because it was a little harder, is setting the derivative equal to 0. And for that I take 3x squared minus 10x plus 4 and set it to 0. And I did not design this problem to be factorable. I just made it up completely randomly. And I assumed that we would probably need the quadratic formula to solve this. Right? That's a quadratic. Okay, so we all know the quadratic formula. It is negative b plus or minus b squared minus 4 times a, square root of b squared is 4 times a times c all over 2a, which equals 10 plus or minus square root of, what is that, 12, 40, is that root 52? 12 and 4, 48, 50. I believe that's root 52 there. All over 6. And then I'm going to need some help here. Root 52 on the calculator. It's about 7 point something. 7 point what? 20? We'll just 7.21. Let's go 7.2 because we're not trying to put a man on the moon here. Let's just round it up, round it a little bit. 7.2 over 6, okay? That good with you? And now we have two different scenarios, don't we? We have 10 plus this divided by 6, and then 10 minus this divided by 6. Agreed? Okay, so I need to do both of those. So I do the plus case, and then I do the minus case. So when I do the plus case, I get 17.2 divided by 6, which is 2.9-ish, okay? And then if I do 10 minus 7.2, that's 2.8 divided by 6, which is 0.47. You with me? These are the two values of x that I would have to plug into this to make it 0, right? These are the two critical numbers. Yes? Now, I'm supposed to, on step 2, take these and plug them, wait, no. I'm still in step 1. I'm supposed to now take these and plug them into what? I'll go back to the steps. Find the critical numbers of f. We've done that, haven't we? Evaluate the original function, f, at those critical numbers. Something interesting is happening at these 2 points, right? The slope of our tangent line is 0. We could potentially have an absolute max or absolute minimum there, right? We could. So what we're going to do is we're just going to take these values and plug them into the original function and see what values we get out. Then we're also going to, on step 2, plug in the endpoints. Why is it that I should plug in the endpoints? I could have an absolute maximum at the endpoints too, right? So what I'm doing is I'm comparing and trying to figure out what's the biggest and smallest. Now, does anyone see an issue?
It's
2.9 is what? It's not in our interval, okay? So we do not want to plug in 2.9, right? We're only supposed to look between -1 and 2. So we are going to scrap this not in -1, 2, right? That's why we're scrapping this one. 0.47 is. Yes? So I'm still in step 1 here. I'm going to evaluate my original function. Still in step 1. What is f of 0.47? So you have to do like 0.47 cubed minus 5 times 0.47 squared plus 4 times 0.47. And I'm sure someone's already done that for me. No? 0.88? Okay, we'll see if anyone else gets 0.88. We're going to check this with the graph anyway. Let's go with 0.88, all right? Anyone else got that? Yes? Okay. So, and remember, we rounded here, didn't we? So this is approximately 0.88. All right, that's step one. This is the y value that comes out when I plug this in as the x coordinate. Got it? Now, step two is to evaluate the original function at the two endpoints. My two endpoints were 1 and 2. So that should be a little easier to plug in. This is -1 cubed minus 5 times -1 squared plus 4 times -1. What's that? -1. This is -1. And then this is 1, but then times -5, so -5. And then this is -4. So looks like we're getting -10 there. Right? -10?
Yeah.
Okay. And then if we plug in 2, we're probably going to get a pretty big number. Let's see. 2, let's see, minus 20, and then plus 8. I believe that's what I'm getting. Just plugging 2 into this. So 8. 2 squared is 4. 5 times 4 is 20, so minus 20. And then plugging 2 in there, we get 8. Yeah. So that comes out to be what? -4. Okay, so let me box the answers I got here. I got -4, -10, got 0.88. Those are the three answers I got, right? So step 3 is to compare them. So what is the global max? This is step 3. What is the global maximum of this function? 0.88. The global max is 0.88. And the global minimum is, not global, sorry, this is a local. Wait, we are on a close interval, sorry, just had a brain fart there. Global minimum, what is our global minimum? -10. When we say global, it's the same as absolute, right? Yeah. Global, but global means just here, right? This is our entire universe of numbers, right? Okay, so let's verify this with a graph. I'm going to go to, what is that, Desmos? Yeah, that didn't want to go. Yeah, right. Why does it not want me to do anything here? What did you do to my computer, Diego? Okay, the problem is, whoa. The problem is that browser sucks.
Maybe it's that guy with the monkey thing.
With what?
The guy with the monkey thing. Remember at the beginning of the semester, someone like replaced like your pages with like,
Oh, yeah, yeah. The YouTube thing? Maybe this entire network is just no good. There we go.
probably.
All right, Desmos. There we go. So I'm just going to type in that function. It was x cubed minus 5x squared plus 4x. All right, so that's it. And I can't see it.
It's probably flash loading or something.
There we go. Okay, so now what I'm going to do is I'm going to restrict my domain to between -1 and 2. And let me zoom out a little bit. Whoa. Oh, you know what? I think I have to do the restriction over here. No?
Yeah, I think you are. You have to put a comma and then you have to put the restriction.
Comma.
At least it's not latex.
That didn't look like it.
I think you have to do it on like, is less than x.
Yeah.
I think that's what I had.
Let's not worry about it. Let's just come back to this and do -1 to 2 and -20 to 5. There we go. All right, that's good enough. So the edge of the screen is where we have the cut. All right. So is it obvious to you that the lowest point is over here? And the value of that point, the y-coordinate, is -10, right? And then the global maximum is right there. And that point, it looks like, is about, I don't know, 0.88? So this is 1, 2, 3, 4, 5. So it looks like about 0.88. Now, what I think is also important with something like this is not only knowing what the value is, but where it happens. Okay? So when you give me your answers, here's the way I want you to give me your answers. I lost that page, didn't I? Who cares? Just leave it like that. Okay, here's the way that I prefer your answers. When you give me global max, don't just give me 0.88. Give me this instead. F of 0.47 equals 0.88. Instead of giving me -10, give me f of what? F of -1 equals -10. That's the way I would like for you to state your global max and global min. Because again, it gives you a little more information. It tells you the x-coordinate at which it happens. Questions? All right, I think we need to do a problem that has a little more bite to it. Because that function was too easy to differentiate, wasn't it? Yes, it was. All right, let's try something else. How do y'all feel about the concept? Pretty straightforward? Okay, how about this one? Yeah? How about f of x equals x root 9 minus x squared on the interval -2, 3. Do y'all want to look at it first or no? Hmm? No, I had no's already, so I'll wait. You got to be quicker, man. Got to be quicker. Okay. We have to make sure that this is a continuous function on a closed interval. Is it on a closed interval? Yes, because I give you the closed interval, right? But is it continuous? And that is not directly clear. Because you have a root there, don't you? And root functions could be undefined. So let's consider this in here. We would like to know what would make that negative, right? Because that would be bad. Another question we could ask is, instead of saying where is it bad, where is it good? So either way you can look at it. I'm going to do it this way. I'm going to say, when is this bigger than 0 or equal?